Hello, and welcome to the telemetry talk of Heinz-Joachim Wölke from the Raumfahrt, the alternative space agency. And just before we start, I would like to do some public service announcements. Please take your trash out when the talk ends and leave comments in the Fahrplan so that we get your feedback. And without further delay, I give you Heinz-Joachim Wölke. Please give him a round of applause.
Yeah, welcome to my person. I'm engineer in avionics, and now I'm retired, so I have time to get new work on things I like to do. So rocketry, and my special item is telemetry and electronics, communication, and electromagnetic compatibility. And I'm ham radio. My call sign is DK2 Uniform Oscar. And I'm also active on a large, on a radio telescope with two large antennas. So, können wir mal anfangen. These two antennas we suppose later use for a ground station for telemetry reception if we are going into space. In the moment we have rockets like you see here. They have been got an altitude up to 2.5 to 3.5 kilometers, and we have a lot of launches now and successfully got these rockets back, and we could get some data via the telemetry of this flight. Okay, let's begin. Our motivation is the retrieval of information essentially for every experiment. Therefore, electromagnetic waves are the natural choice for the communication, and sometimes only the mean to retrieve the flight hardware afterwards, because sometimes the rocket falls down without the parachute and or disappeared in a lake or in mud, and sometimes we had the problem. It took about a year to get it back because some forestmen found this rocket, and so at that time we did not have any electronics on board, just flying the rockets. Yeah, the definition of telemetry, this is coming from the Greek language. Tele means remote, and metron, measurement data. It is remote measurement and reporting of observable information. So we are not only shooting our rockets in the sky or in the space and watch them, because some members of our club are also make model rocketry. These rockets fly only a few hundred meters high, and because you want to see how it's flying. But our rockets, they fly, the last ones fly about 1,000 kilometers per hour, and So you see only a few seconds, and then you can't see the rocket anymore. You can only receive the real-time data if everything runs fine. Yeah. So some milestones in the history. 1845 was done in Russia, the communication between the Tsar Winter Palace and the army headquarters. Of course, they did not have wireless communication, but they made the communication on wire, telegraphy or telephony. Then 1874, transmission of weather data and snow depths from the Mont Blanc to Paris. This is also very interesting about a good feature to use the telemetry. Was ist jetzt? 1901, an American got a circuit sending synchronized rotation information. That means you can remotely control, turn something, and at the other end it turns also some resolver. Then 1906, a set of seismic stations is installed transmitting the Pulkovo Observatory in Russia. So they could find when there's earthquake, they could get immediately this data and they can do some action, some reporting and so on. 1912, Edison develops a system to monitor the power grid. Yes, it is very important to know whether the power is at all places solid on. Yesterday we had, or the other days, sometimes the power was off here, and so we could not work anymore. Then you see how important power monitoring is on. The whole night yesterday, the power came not back at the outer space where we are in the moment in a tent. So 1913, extensive of telemetry observed logs and water levels in the new-built Panama Canal. Also, you can see there, it's also important because this Panama Canal was a very big adventure and to optimize the whole trade in the world. Then 1930s, wireless telemetry developed independently in France and Russia. So this is wireless telemetry instead of using it by wire. 1942, first real-time rocket telemetry systems for the A4, yes, the so-called also V2 rocket. And all things which we have today, they had in analog technique also at the 1940s years. Today, we have different applications for telemetry. For instance, everybody knows when watching to motor racing as Formula One, so you can directly see what the pilot is doing and also the data from the engine and where there are some failures and so on. Agriculture, yeah, so they can measure different weather propagations, and they have remote stations to show the situation on the fields, temperature and so on, water, raining. Water management also, yes, we have many storage of water, and so it can be checked, and so that everybody can open the crane in a correct way, and not like oh, now there's nothing more, so they can remotely check whether everything is in the right function. Yeah, then a large field of telemetry is, of course, in defense, in space, and resource exploration systems. So when, for instance, oil platforms, they will be also checked, the data will be checked by telemetry, for instance, and defense, yeah, electronic warfare is also a big, place for telemetry, and but some of these uses also still wires to control some missiles by wire, because wireless communication sometimes can be jammed and also faked. Yeah, rocketry, this is our special region. We can measure all the important features for the flight. During the flight, we can get the speed, the velocity, the temperature, pressure, and sometimes we have a so-called Prandtl sonde. This is what also on the aircraft, they have a small pipe in front, and then we can measure the speed of these, yeah, the same as on flight test, rockets, and it's also a vehicle which is flying. The whole flight test, for instance, when a new aircraft will be tested, they need also telemetry data from many different sensors, because the pilot cannot watch to everything, and so on ground the engineers and technicians will monitor this and storage and get results by it. Yeah, enemy intelligence, this is also a wide field, secret services, and they watch to everything. I think it's also here at the Chaos Communication Camp, a big field about what's done with watching to everything, yes, RFID and what else you ever use, or the GSM telephones, because the GSM technique can be also used for telemetry in many fields. Energy monitoring, yeah, this is of course power plants, for instance, and many other things which we need for the energy, the temperature of a power plant, and see whether there is enough fuel, and so on. yeah, resources distribution. This is like water management in other resources. We can directly bring the needed resources to that place where it can be used. In the medicine it's very important to have remote information because, for instance, when they do operation, they maybe monitor it behind the operation room, what's going on. Therefore, it's also a big field. Fishery and wildlife, you can put some transmitters on fishes, for instance, on wheels, and also some animals get a transmitter, and you can monitor where it's on which location, or the movement of wild and wildlife animals, for instance. Retail business, we have in many supermarkets today. They monitor when you are going out and you have something in your pocket. There is a little chip or a little electronic, maybe only a printed antenna with a diode, and it's generating a spectrum, and then a warning goes out that somebody takes some goods with him and did not pay. Law of enforcement, for instance, when criminals shall be observed where they are, they get some electronics, and they can be monitored whether they are not leaving the environmental, or you can also see on the borders whether there are persons walking over the border without permission. Electrical energy providers, of course, as was said, everything will be monitored. The distribution of the power, for instance, when we have today the wind power stations, they should know whether these, on a central point, whether these power plants work correct or not, and they must plan to make another power plant, maybe with brown coal or nuclear plant, perhaps. In these days, still possible, but in the future, maybe not anymore. Not in Germany, perhaps. Yeah, the Arabs, they like the falconry. They have the birds, and they get a little transmitter, and so they can make a direction finding when this falcon is disappeared. And because, as I know, I have worked very often in Arab countries, also in the Emirates, and they have very expensive falcons, and of course they want to have these animals back if something happened with it. Of course, all tests where where it's, for instance, dangerous, where you cannot directly look to it. You will have cameras, sensors, electronic sensors, different physical data remotely, yeah, and we can watch to a test. For instance, you have perhaps seen yesterday when we test hybrid motors. It is sometimes good to get a little bit away, because such rocket engine can also work in a dangerous phase, and it's better not to be too close to it. Yeah, the real-time communication is the very important feature. By the rockets, we want to know directly what's happened, and in our new Arguna 4, there are some pieces here. We have a system with parachute, and when the parachutes are out, there is a GPS receiver, the antenna on one line, and so it will be, the data will be sent down to ground, and so we know directly what's happened with the rocket and where the position may be going on, and then we can, if it's then down, we get the last position, send it. Sometimes, as I told you, this rocket may disappear, because so it's good to know the last position before it reached the ground, and because we have some area where we launch our rockets, there are around some lakes, and we will have about in a month campaign in Denmark, in Tranum. This is directly at the North Sea, at the Kattegat, and there is a place we can only launch our rocket directly away from the boundary of the country, so it may fall down into the salt water, but there is a boat with a direction finder on board, and we have a balloon which will be ejected, so that hopefully the rocket will not go under the water, and we can find it back, because our new project is planned about 8 kilometers, and it will hopefully fly about Mach 2. And because this motor, which is laying there, will have 1 ton of thrust, and so we hope that it will run very fast. Remote control, this is another feature of the telemetry. Before I talked about receiving data. This is a good field, but for instance, if something goes wrong, It can happen, for instance, when the ignition of the motor is not getting fast enough, then the rocket will not launch straight into the space, and then it may fall down, and it will harm some facilities on the ground. And so a plan is to have a switch off for the flight. But in the moment, we are doing this. We are not doing this. This means flight abort. This is the function also. Yeah, as I told you, we have the telemetry, and we have a special radio beacon on board also, sometimes in a fin, sometimes inside the body of the rocket, and then we can go with directional antennas and receiver. We can, on a certain ground, on a certain area, we can make a direction finding and get the bearing and walk to the rocket and hopefully find it also. Therefore, a radio beacon is used. So here I have a circuit diagram about our electronic, our avionic. So we have here, we have two sections. This is the nose. Here comes the nose of the rocket. Here we have the telemetry transmitter, and here is, in the moment, the test antenna. The planned antenna I will talk later on about will be a so-called patch antenna system. But for our tests, this was enough. So we see here the RILE button where it's on the launch system. And here inside we have this DPU. We have the inertial navigation avionic that measures the data. And then analog digital converter, and then we have between the upper and the lower section. Here in this section you see there is the parachute inside. So this is on top of this, and the lower section here did not have time to pack it out. So, yeah. So here it is. This side here, there is the power supply inside. We have batteries here, a set of batteries, which will be directly above the engine, the rocket engine. Moment. This is the exhaust here, this graphite, and this is the coupler on which the electronic will be put on. Here, this is this side. Here we have the test antenna in the moment of the radio beacon. And we have here some cables. On this, there is the RS-232, goes to the upper DPU. And on both DPUs, we have SD RAM cards. So if we get rocket back, we can also get the data here without telemetry. We can afterwards also compare these data which were received by telemetry, because sometimes telemetry makes also problems. I will talk about later on. So we have here the other analog digital converter with different physical sensors. And then it goes, then we have the GPS. I already talked. The GPS antenna is in that section. Let's see. And the shockwave other side. We had made some tests during the last time, and you see here, this is the GPS receiver hanging on the shock mount, and via this telemetry, you see here the connector goes here inside, and then we get it to the DPU, and all this data is transmitted, is fed to this transmitter. This is the transmitter, the telemetry transmitter, with the antenna to the ground. So here I have a various set of different antennas. This is a 70-centimeter antenna, which we have used also in Denmark for receiving the telemetry data. And we could get the whole flight, we could get the data in, we put it in like in this way on a support, and at the end, I will show from this campaign some photos. And also we use this antenna when we will use for the higher the higher altitudes. For the next project, we have more gain to receive. It's also 70 centimeters, which means 433 megahertz. You know, there is a band that's called ISM. This is industrial, medicinal, and science and medicinal band. This is 433 megahertz. So this can be also improve when we launch more than 10 kilometers our signal, because we need a in all phases, because we don't know in which phase the antenna is. All antennas have a characteristic, and sometimes the signal strength drops down. Then it's very good if you have a gain antenna, and you can improve the signal as well. Yeah. Here is, for instance, 1.3 gigahertz antenna made by a printed board material. Here is this is for 23 centimeters, which is also used for some reception. And I have also for 2.4 gigahertz. Let me see here. I have a mini camera for an experiment. This is the antenna for the ground station. See, this is cappuccino, and it has also the radome. You can see there is inside the probe, and this antenna has a gain about multiplying by 10 the signal strength. So very easy to construct. And here you see there's also an antenna made by printed board material, just soldered here. And then I have this small camera. You can buy this. It transmits on 2.4 gigahertz. Normally there is only a wire antenna, and the range is about 300 meters. But I integrated here a coaxial connector, and there are some power amplifiers which can be used to increase. I have increased with a certain power supply with a power amplifier up to half a watt, and then it's also good enough for 10 kilometers and more. Yeah. So, and all this I receive here with, I have here for my notebook an interface, TV interface, so I can receive real-time pictures. We have also on our homepage, we have some photos, some videos. You can, if you like, www.alternative-raumfahrt.de. There you will find also some videos. We have a mirror on it, and we can. Half of the picture is looking to ground, so you can see when the rocket is lifting, and the other is around, and you see when this rocket is hanging on the parachute and tumbling and so on. It looks like, so it's not so good if somebody would sit inside or an animal. Yeah. So this is in the moment about the telemetry, some hardware. I have also receivers with me and direction finder. Yeah, and the next antennas I will design are the patch antennas. This is made of double-side printed board material. So we can fix it on the rocket's body, and it is for the high speed. If we reach the 2 Mach region, my wire may be melt and will be damaged, and we will not receive the data. Ja, I think the next, which is very important, when we finished the design, we made our test, and then suddenly we were astonished. We had good signal strength, but we had corrupt data. What was the reason? The reason was the telemetry was blocking the GPS receiver because the active GPS antenna was, when the telemetry is transmitting, was blown off for a while, and then the data, we get only confused data. So I had this in my house, shielded everything with some aluminium paper and some ferrite components and feed-through capacitors, because here, for instance, this transmitter in our first test phase was not in a metal housing. It was just the way, and when it sends, the GPS was finished. Yeah. And also from the other data, we got some problems. Now we have for different for the different sections, we have also different power packages. So because there are a lot of ideas we got. So what is the principle of the electromagnetic compatibility? This is also the reason why we are here at outer space. We often have no WLAN, wireless LAN. From time to time it fails, and I think it is the different systems work together and block each other. So we have very seldom internet more than an hour. Yeah? So more than an hour stable, then we must look for another wireless LAN, and then it's of course this is the Antonov 2, which is okay. The Antonov 2, I had the opportunity 2 years ago fly with it. It makes 1,000 PS or horsepower. It's a very hard machine. So, okay, it's away now. Good. Electromagnetic compatibility. This is my special region here in our club, and I found out many things. So we have the source and the victim. That means what I told is like the example with the GPS. The data will be transmitted, but the GPS is out of synchronizing, so no data, no valid data. Yeah? So machen wir das nächste. So what can we do? Of course, shielding. RF filters. I have built a lot of filters, so-called notch filters. They are made of coax cable in a certain length, quarter wave length, or times quarter wave length, and it will drop the unwanted signal sometimes more than 1,000 times down. So it will make, so I have it in front of the receiver, the GPS receiver, in front of the telemetry, which is on the 2-meter band, also blocked once our DPU. So because we had the harmonic of this also making problems, so I built band pass filters, yes, which only allows the wanted frequency to pass through, it drops down by 30 or 40 dB, so 1,000 to 10,000 times down. And then we have the notch filters. I can just put the length of the cable. I have measurement equipment. I cut the length of an open coax quarter wave length, and then there is a notch, and so the unwanted frequency will be dropped down 1,000 times and more. Farad choke is very good. You see here on the normal computer power supply, all these round things, or on the monitor. Yes, so normally here I don't see in the moment, but these are the Farad chokes and Farad beads and so on. So mach mal weiter. Feed-through capacitors we have here on, where is it? Here. Here are it's now. Feed-through capacitors here, so the RF which is inside shall not harm the other systems. Here you can also see our electronics live here. So proper grounding is very difficult, because this is also a problem, because as you see, we have our housing for our electronic is on wood in the moment. This is a prototype, of course. The next generation, we will make it on metallic, and so we have, and also the length of the cable, for instance, is also sometimes a problem. Here you see this is a sensor for pressure, which is here hanging around there, and here you see there is a notch filter, a so-called quarter wave stub. This is this here, the quarter wave stub, just a coax cable. But you need measurement equipment to find out the correct frequency and how it works. Ja, haben wir noch einen Punkt? Do we have more points here? What? Finish? Also, high quality cable. Yes, you can. Okay, you can get cables. Each cable is not the same. It looks maybe the same, but it's inside. It's not the same. So there is a shielding and so on, and for instance, in some RF components, there is resistant material inside of the inner conductor to reduce some bad functions. So yeah, this. Okay. Yeah. So now I have I have some pictures of our start campaign in Denmark. This Arguna 2 rocket was launched there. In Denmark, they have a school project. They built 50 or more rockets in this size, and the pupils built some experiment, and they make a funny colors design on it, and they start one after the other, and we were the pop stars with our rocket. That's why we have tomorrow I will show also the launch of this rocket, and the Danes, and they say, oh, but it was very fast, and we couldn't get it so quick back because it was a shooting area, so we had to wait some hours to go on. And there was also another problem. They have target display system there for the shooting, and they make some spurious signals, and we could not make direction finding because we have a lot of peaks on all frequencies there. So this is also sometimes a problem, but in case I walked through this area and suddenly I saw something orange because the flowers in that region do not have the orange color, and that was our parachute. And so nearly in a mud place, I found our rocket back. So, Malte, das war. Here you see this antenna. It's mounted on a support. And, we are preparing our launch we had a work hall there, and with all machineries and measurement. We spent a whole week there with the Danish challenge, DSC group, the DSC Danish Space Challenge, so it's called the club there. And they're very polite people. So, mach mal das nächste. So we're preparing the rocket. It's a little bit, I hope you can see this, okay. This is the avionic system here, integration, stop. Okay, mach mal ganz schnell ein paar Bilder durch, so 20 pictures. Here you see the antenna. Here we test a GPS receiver. Here the campaign with the pupil. So young people also are interested in rockets. Here my antenna. So David here, he's sitting here on his ground station. This is the ground station, also a development equipment we used for the ground station. So preparing everything with the antennas and so on. Here, next photo you will see there is a small Foxy beacon, radio beacon inside on 70 centimeters, and we could make direction finding. So here our youngster, today he will be 3 years old. His birthday is today. He was also with us. This is the GPS position of the antenna of the rocket by a tracker. So this is the parachute you can see, which I find. So now it's finished. Yeah, I think you have any questions to it?
I think we're probably run out of time, and so there will be no time for questions, but I think if the people come to you outside and you can answer every question, and I thank you very much. It was an interesting talk and a lot of hardware to look at, and please give a round of applause.
Thank you very much.
Thank you.